All right, welcome back. Last time we had covered the idea of what an atomic vector is. So, as a review, a vector in R is not like the standard mathematical definition of a vector. A vector in R is a set of elements that are ordered. Okay, so any collection of objects, a collection of elements that we could assign an order to, that's going to be a vector in R. And there are vectors where every single one of those elements are the same type of object. So, for instance, they're all numeric, or they're all character, or they're all logical, or something like that. And those are going to be atomic vectors. And if you have a vector, a set of ordered elements, where some of the elements are logical, but other elements are model objects or plots or something else, then that would be a non-atomic vector, but they're both vectors. So I've got atomic vectors over here. So I'm going to go back to this image. I've got atomic vectors over here, and that's a set of ordered elements so that all of the elements in that set are the same type of information. And then maybe then over here, a non-atomic vector or a list is again a set of ordered elements, but this time I have the restriction removed, so they no longer have to be of the same type or the same class. All right, so what are the types that an atomic, or the classes that an atomic vector could be? Well, that's what we're going to cover a little bit right now. For this class, really, I want to talk about four of these. I'm going to mention six, but I'm only going to talk about four. So and these are in order of complexity. So we've got the logical, and this is order of complexity in terms of what we would actually interact with. Like whenever we're writing our code, we're going to be interacting with four different types of atomic vectors, and we're going to have these in order of complexity. So logical is this is like the most basic type of information that we're going to have, that we're going to be working with, and it's simply just true or false values. And you can imagine that the complexity of information that you could store with just a single true or a single false value is not a whole lot of it's not terribly complex information. There's literally only two possible values that it can have. It can be true or it can be false. Okay. Now, we've got integer vectors. So this is a step up from logical in terms of complexity. An integer vector is, as we learned in middle school, it's just the set of whole numbers. But in this case, R includes both the negative whole numbers, the positive whole numbers, and also R includes zero in the integers. In terms of like a purely mathematical definition, the integers start at I think it's yeah, I think it's the integers. The set of integers starts at one and then goes up to positive infinity. But in R, it goes from negative infinity all the way to positive infinity. It includes zero. It's just all of the whole numbers. So things that you could count with, if you will. And these are obviously more complex than just true or false. But in terms of the amount of space required by the computer to store this information, it's relatively simple. We're just saying, okay, well, I'm going to take this integer and I'm going to turn it into something base two, and then I'm going to store that integer. So if I need to do 1,000, then I'm going to find out what's the largest multiple, like what's the largest power of two that goes into 1,000. I think it's gonna be like 512 or something. And then the next largest power of two, which would be 256. The next largest power of two, 128. Actually, we can just do it. 1,000 in binary. Um, okay, so what we're saying is, I think this is five. There's a 512, and then there's a 256, and then there's a 128, then there's a 64, then there's a 32. Sorry, this one would be for the 32. There's not a 16. There is an 8. And then there's not a 4, there's not a 2, and there's not a 1. I'm pretty sure that's how you read that, and I haven't done this in a little while. But anyway, so that's basically what we would do is the computer is going to say, well, 1,000 in integers is just a whole bunch of trues and falses. So is there 512 in 1,000 true? And then I add that to 256, the next power of two, and then I regard that as true or false. So if you think about like how a computer actually works with information, computers, I hope everybody knows that computers work in binary, and so that means zeros and ones. And the reason for that is the binary can represent either the presence or absence of an electrical signal. Okay. So if there's electricity coming through in this interval, then that represents a one. If there's no electricity coming through in that interval, then that represents a zero. So everything in the computer is represented as there's electricity there or there's not. And so that's why one of the things that when we're talking about like true versus false, this is kind of like it's absolutely not actually getting down to machine level binary, but it's very simple in terms of how it's easy for a computer to interact with trues and falses. And then integers, it's also relatively easy for a computer to interact with integers. Okay. Now we move up from integers. So integers, we said from negative infinity all the way up to positive infinity, including zero, but all of the whole numbers. So 1.5 is not an integer. It's not allowed in the set of integers. But that's where we get into numeric. So this is the set of all of the real numbers. So this includes 1.5. This includes pi. This includes e. This includes phi, the golden ratio. This includes the square root of 2. This includes the natural logarithm of 30. Like all of these numbers that either need a whole bunch of decimals to represent them, or they need an infinitely many number of decimals to represent them. Now, representing the square root of 2 in the computer. So what we can do is we can say square root of 2, and it's going to round it. It's going to give me this information out to 1, 2, 3, 4, 5, 6, and then 7. So this is 7 numbers, and then there would be a positive or a negative number. There's an imaginary plus sign. If I put a -1 right here, let's do -1 times the square root of 2. Notice here, I've got the same amount of information, but now there's a negative sign in front. So this is saying that there are 8 slots or 8 bits, if you will, of information that the computer is going to use to represent the square root of 2. Okay. And so it's the sign, whether it's positive or negative, that's 1. And then there's a number, whatever the value is ahead of the decimal place. And then 1, 2, 3, 4, 5, 6. That's going to be 6 plus 1 plus 1. That's 8 bits of information. So this takes a lot more information than just the integers. And the reason why is because I have to represent what the negative sign is, positive or negative. I had to represent the negative sign with the integers as well. But the real numbers, I don't just have to represent this one number right here, but I also have to represent all of the decimal places as well. Okay, so it's more challenging for a computer to do. Let's see what pi looks like. Yeah, again, similar story here. We've got 6 decimal places. Now, part of this is due to our rounding. R is going to round the number before it shows it to you, but the actual, let's see if I do question mark pi, these are built-in constants. Let's see the ratio of the circumference of a circle to its diameter, and does it tell me? It doesn't tell me, let's see. Yeah, I'm not sure how many decimal places R uses internally. You can probably find that out too, but I don't think we should care very much. Anyway, R is going to use a lot more than 6 decimal places, but it's only going to display 6 decimal places to you. And then finally, I'm going to skip number 4, complex, because most of you are not electrical engineers. Complex numbers come up in electrical engineering because you have imaginary numbers there. Otherwise, we're not going to be needing to deal with like 1 plus 4i or whatever. So I can't think. Oh my goodness, when was the last? I think I used imaginary numbers for it was a biomedical engineering something or another. probably 10 years ago was I think the last time I did imaginary numbers in R. It rarely comes up unless you're working with engineers, particularly electrical engineers. It comes up for electrical engineers a bit. If you're not working with them in like a health science, biomedical engineering related context, you're probably never going to run into complex information. Then that's okay. And by complex, I don't mean like I mean like the complex plane of numbers. So there's the real part, and then there's this 4i, which is in the complex part. A lot of the data that we deal with in health science is quote unquote complex, but I mean that it has an imaginary component. Most of the numbers that we deal with, I can't think of any data that we would be dealing with in public health that has an imaginary component to it, unless we're talking about bioelectrical impedance or something like that, where we have real monitoring data on a person that has to do with like electrical fields or magnetic fields. Um, and again, you're going to be working with an engineer. And so if you need the help, they should be able to help you out with that stuff. Finally, most complex information that your computer is going to store that can be put into an atomic class is character information. This actually is storing like letters and numbers and so forth. And if you think about it, there's 10 digits, so 0 to 9, plus there's 26 uppercase letters, there's 26 lowercase letters because R is case sensitive, and then there's a whole bunch of other symbols, okay? So there's something called the ASCII codes, and you can store a whole bunch of pieces of information inside of a character vector. And this is the most complex because we've got all different kind of combinations of characters that can be stored here, and we need the computer to be able to represent this. So character is the most complex. So again, for what we're going to use in the health sciences, logical, then integer, then numeric, then character, the four classes of atomic vectors. Alrighty then, and next time we'll pick up with a couple examples. All right, see you soon.